Let's get rolling. Okay, couple of items. I want to show you a couple of drawings that we have. Just want to pass them around, and I just want to show you different sizes of drawings. So, in drawings tend to have letter sizes, and I believe the 8.5 by 11 sheet of paper is what's called an A size. This here is called a D size print. D. So you might hear that in industry. We need D size prints, or we need E size prints. They do it a lot in construction and sometimes in aerospace and mechanical engineering, because sometimes parts get too complicated to show on a little piece of paper. They have to plot them on a big piece of paper. These were parts utilized by our BioServe Center here in aerospace engineering. They send a lot of stuff to space on shuttle flights and such. They're trying to work towards commercialization of space. Send that around. So I'll pass this around. So this is a D size print, and it's got some different views that I was showing you. So here's a section view, and I believe they have a detail view over here. So I just wanted you to see how that's used in real life. So I just pass these around. This one is same thing, but in E size print. E. So they get bigger as they go. E size print. Okay. Send that around. You guys can just look at that while we're talking. All right. All right, we're going to move into we're going to move a little bit away from SolidWorks for a bit. We're going to talk about some engineering applications, mostly for aerospace, but also for mechanical. So we're going to start with fastening. Fastening is something that our seniors come to us all the time not knowing how to do. Don't really learn about it here, so in your curriculum. But it's pretty important when you get to your projects courses, because you have to build things and stick them together. So hopefully this course will make you smarter when you get to your senior projects. You can tell your teammates what's up when it comes to fastening. All right. So there's quite a few different methods for fastening. Oh, by the way, this PowerPoint and the next one will be are on D2L for your reference if you want to download it and never go back and look. This is really important stuff for engineering. During your career, you can fasten things a lot of different ways. The most common is mechanical fastening. That's with all kinds of mechanical fasteners. Bolts, screws, pins, retaining rings, gears, rivets, all kinds of crazy mechanical fasteners out there. There's also adhesion. We'll talk about this later. This is a common mistake of students, is to trust glues. But adhesion can be done with glue, tapes, resins, epoxies, soldering, brazing, etc. Okay? I can't tell you how many times engineering students have trusted glue just because of its brand name or their perception of what glue is. In aerospace, it's common. Has anybody ever heard of Hysol? Hysol is kind of an aerospace-y type glue manufactured by 3M, and students rely on Hysol as if it's ultimate strength, infinite strength. Well, I glued it. I Hysoled it. It's the best glue there is. It must hold. Well, that's not true. In engineering, you have to look at all the different forces involved. If you have a tensile force on a glue joint, well, how you have to model that glue joint. How strong is that glue? Well, glues are difficult to model. It's very easy to model a mechanical fastener because it's got a geometry. It's got a material property. A glue, may not even be sure about the material property. How about how it was adhered? How was it applied? What surfaces was it applied to? What preparation was done to those surfaces? What temperature and humidity was it when it was applied? How was it mixed? At what speeds? With what tools? In what environment? So glues are difficult to model, and therefore you need to be very careful when you're making claims or assumptions with things that are adhered together using glue. Okay? My most famous example was from years ago. We had this really good senior projects team that built unmanned aerial vehicle, about a 6-foot wingspan, maybe 4.5, 5 feet wingspan. Really cool plane. Built it from the ground up. They went to go flight test it, and it's going down the runway, and the wings took off, and the fuselage didn't. Okay? Their answer at the end was, well, the interface between the wings and the fuselage was glued with high-sol. And their answer was, but we high-soled it. Well, that doesn't mean anything. You need to model the lifting forces on that body and then bounce that up with your design. What was designed to withstand those forces in order to lift that plane into the air? They didn't do any of that. They just glued it and said, it's glued. Well, you can't do that. Okay, that's a bad thing to do. Don't do that.
Is there ever a case where glues would be good to use?
Oh, sure. I mean, they use glues all the time. So, for example, in the Dreamliner, the Boeing 777, I don't know if you've ever seen it. It's a carbon fiber fuselage instead of an aluminum fuselage. The difference is, when they build that sucker, you can probably go on YouTube and look at the machine that rolls it on there. Okay? When they build it, it's in a warehouse that's temperature and humidity and gas composition regulated. The machine that rolls that carbon out is applying an extremely precise and accurate layer of the resin. The resin is mixed by a machine very carefully, down to milliliters of the epoxy and the hardener. All those processes are very tightly controlled, and if you do all that, then you can use empirical data on those manufacturing processes as an engineering design parameter. But if you yourself go down to McGuckins and buy some Gorilla Glue and squirt it on a couple of sheets of aluminum and smear it around and stick it together, you can't trust that. Okay, because you haven't tested that bond in that environment on those alloys of aluminum without any surface preparation, without any cleaning. And today is 28% humidity probably out, but in Colorado at this time of day, it's usually 7% humidity, right? Or maybe it's 100% humidity out. So what temperature did you apply that at? When Boeing makes that airplane, all those parameters are tightly controlled, and then you can trust your designs, okay? But you guys aren't going to have those situations, most likely. So be careful. You can put things together with magnetism. That happens a lot. You use that in design a lot. Welding, so it's actually melting two similar materials together, as opposed to soldering and brazing. That's different. And then there's others. You can use gravity in a design. It works all the time, every time. You can use friction. And you can use things like centripetal force. Aerospace, spacecraft use that all the time. Okay? You can stick something to the wall of an aircraft or a spacecraft if it's spinning, right? You're going to have an acceleration on it. It'll work. The most common is mechanical fastening, so we're going to talk mostly about this. We're going to talk a lot about bolts and screws, mostly screws, because you're going to use those a lot, and most of you don't really know much about screws. You may think you do, but you don't. And I know because I see you when you're seniors, and you do crazy things with screws that aren't okay. Bolts and screws are kind of in life the terminology is used interchangeably. They're really not technically interchangeable, but people use it that way. there's kind of a gray area as to what is a bolt and what's a screw. According to Machinery's Handbook, a bolt is different from a screw in that you have to use, the threads are tightened by another piece, like a nut. Whereas a screw screws into threads, doesn't need a nut. Okay? But that's not how the terminology is used in industry. So you probably don't want to pay attention to that. The terminology that tends to be used in industry is small diameters, and by small we mean less than 1/4 of an inch, tend to be called screws. And bolts, since it sounds tough, bolt, you know, that's used for greater than 1/4 inch diameters in general. All right, we have different kinds of screws. We have machine screws. Machine screws have a consistent thread profile, and I'll show you that thread profile later. And they're typically used for fastening things in tension or compression. Wood screws are different. They have a much more aggressive pitch, and their threads are sharper. It's a completely different thread profile, and that's because they're not typically meant for drilling a hole and then screwing the screw in, although you do use pilot holes on bigger screws. But these screws are meant for just jamming into wood, and they need an aggressive, sharp edge to cut through that wood. You'd never be able to do that in a chunk of aluminum or steel. It just can't move that material out of the way. Wood can. You can move the wood out of the way using the screw, or cut the wood using the screw. We also have things called set screws. They have no head, and those are very useful for some applications where pieces have to go together. Okay, and then this is interesting. Mechanical engineers will use this a lot. It's called a shoulder screw or a shoulder bolt. Threads are designed to be outstanding performance, very strong in tension and compression. If you pull this way or push this way, these threads can handle those loads very, very well. Okay, and the reason is you get, with a thread, you get all this additional surface area. So if I'm pulling this way, I've got all this surface area resisting that force, as opposed to if I just had a round pin, all I've got is that surface area, the circle. With a thread, I increase that surface area by quite a bit. Okay, so they're very good in tension and compression. But threads are awful in shear loads or radial loads. Okay, so if I have a load this way, why are they bad in shear from this picture?
Small cross sections.
That's right. You've got a huge stress concentration right there. Okay? Whereas if you were on a pin, there's no stress concentration. You have this nice round surface to distribute the load. Okay? So that's what this is for, a shoulder bolt is for. If I want to put two pieces of metal together, but I'm anticipating a radial load or a shear load, I want to have this cylinder here to resist that load. And then these threads, all they're going to do is keep the two pieces together in this direction. So a shoulder bolt is useful in those applications. Be careful when you're an engineer putting screws in shear. You don't want to do this. Okay, I think I go into that a little bit more later. All right, bolts and screws come with all different kinds of parameters. We're going to talk about them. They come in all different head styles. So you've got pan head, flat head, oval, round, button, Philister, hex. Typically all of these are called cap screws because they've got a cap on the top, as opposed to the set screws that don't have a little cap on the top. One that you'll hear more than just about any other is socket head cap screw. And a socket head cap screw is this one, where it has a hexagon or an Allen wrench type drive, but it's got a round cap. That's called a socket head cap screw. very, very common in engineering applications. Not super common in, say, automotive applications where most of the bolts are hex heads. Okay, but in aerospace applications, we use socket head cap screws a lot. Yeah.
Why? I mean, a hex on the outside is nice.
Well, not necessarily. Remember, in aerospace applications, space is tight. Okay, we've got spacecraft that are little, we've got aircraft that are little. We need to bury things kind of tight. All right. There's a lot of times when we want to fasten two plates together, but we don't want interference of a head putting those two pieces together. In the case of the socket head cap screw, I can bury the head into material. Here's my screw. It's hard to do that with a hex head because this would have to be huge in order to get my socket over it to turn it. Okay? So the hex heads are really useful in automotive applications, but you got a lot of room on a car. You know, on little planes and little spacecraft, we don't have all that much room. So we use that a lot. Your two most common ones in aerospace are going to be this socket head cap screw and your flat head screw. Those are really, really common. Okay? We have Phillips drives, different drive types. You've got Phillips, flatheads, this star kind of pattern ones called Torx. That's a brand name. You got hex heads, or sometimes they'll be called Allen drives. You have square drives. You have security drives. And there's others, hex heads. The little McDonald's toys come with little triangle drives so that nobody has the tools, so you can't take them apart, so that the little kids don't swallow them and choke and sue McDonald's. So if you ever get a little McDonald's toy, you'll see they have triangle heads. Yeah.
Could you explain to me why the Torx head is even used? I absolutely hate the Torx because it shears off every single time.
Yeah.
It screws up my tools.
Most of the time, I would say it's because most people don't have Torx drives. So you'll see Torx heads on places where people might be expected to take things apart when you don't want them to, because just about everybody has these drives in their pocket, right? They'll have a Leatherman tool or a little tool on your pocket knife that has these, but you're probably not going to have this. And then if you do have this, you're probably really not going to have that. So they make security ones that have a little button in there, and that way if you have Torx tools, you can't stick it in there. Now you can buy that type of drive, but most people don't just have it, right? Yeah. They'd have to go to the store and get it. And so like on a bathroom stall, people, while they're sitting there, they write on the walls, or they take screws out, or they just screw around in the bathroom, right? I don't know why, but people do it, okay? So engineers have to design around that sometimes. That's my best guess. I don't like them either.
I've wrecked so many different
Yeah, the tips.
Screwdrivers.
Yeah, the tips come off, yeah. I don't know. To make money? Okay, this is really important. We're going to spend some time on this. There's different thread profiles, okay? The two most common are metric profile and unified national, so you can call this American or British Imperial or whatever. It's called unified national. They're very similar. They both work on 60-degree isosceles triangles. So they're the same thread profile as opposed to other thread profiles. But the difference comes in the diameter and the pitches. Metric threads are going to have nominal metric diameters. And when I say nominal, if I have an M5, that means the diameter of that screw is nominally 5 millimeters. But it's not really going to be 5 millimeters because 5 millimeters is a theoretical perfect tip point. Sharp, sharp, perfect tip point. So from there to there would be 5 millimeters. But in reality, if you made a screw like this, those tips are so tiny and infinitesimally small that that material would kind of bend over if you dropped it, and then it wouldn't screw in very well. So in reality, when they machine these, they kind of round off the edge a little bit, and so that makes it just a little bit smaller than the 5 millimeter. So it's nominally 5 millimeters. It's close to 5 millimeters, but it's probably several thousandths, if not 10 or 15 thousandths of an inch smaller than the 5 millimeters. Same thing is true with Unified Nationals. A 1/4 inch bolt will be close, or nominally a 1/4 inch, but it's going to be a little less. Now, all screws, metric and unified, come in 2 basic standards. In this case, we call them fine and coarse. Metric calls them fine and coarse as well, but it doesn't actually say fine and coarse. It's very rare to find that. And in America, we don't use a lot of metric fasteners, so you're typically not going to see the 2 different fine and coarse metric threads. Okay? In metric threads, you will see just one. So it'll be like an M4. Well, it's not just a 4 millimeter diameter. There's a pitch associated with that M4 screw. There's a pitch. It's usually like 0.5 or something. We could look it up. Let's do that. They don't have coarse and fine on this chart. Let's go maybe this chart. Nope. Let's try you see it's kind of hard to find in metric the 2 different threads. Here it is. Here's one. So if you look at this chart, you've got an M4 with a 0.35 pitch, and you've got an M4 with a 0.5 pitch. Okay, one's coarse and one's fine threads. But in America, this isn't very common. Since the threads aren't very common, we just have one. So we'll just have an M4. Now it's one of these 2, so you need to make sure as an engineer that you have the right pitch. But I believe they typically go with the coarse thread here in America. So the coarser thread, they'll just call it an M4, even though it's really an M4 by 0.5. Okay. Now more common is the Unified National threads, and I can show you that. So here you can see, let's say a number 8 screw. It comes in coarse, 32 threads per inch, and fine, 36 threads per inch. Same exact thing as the metric, but it's so common here in America that we usually make a distinction between the 2. We don't just say number 8 screw. We say 832 or 836. Okay? They also come in, and the same thing is true of metrics, they come in extra fine or extra coarse, or extra extra fine or extra extra coarse. Then they have ultra fine and ultra coarse. So you can get other designations, but your standard ones are these 2, and in America there will be one standard metric, which is probably the coarse, and that's mostly what you're going to see. Okay. We have another kind of thread profile, and this is going to be the other kind that you're going to use as engineers all the time, and it's the most misunderstood one there is, so we're going to go over it in detail. and that's what's called the pipe threads, NPT. So, in aerospace and mechanical and even electrical engineering, a lot of times you want to move a fluid, which could be a liquid or a gas, but you want to move a fluid from one point to another. It's so common that you take classes on it, right? Who's had a fluids class? Anybody that's a junior or senior, I bet. And every engineer in here, through your curriculum, will have a fluids class. I guarantee. I even think electrical engineers have a fluids class. But mechanicals definitely do, and so do aeros. Okay, so you're going to want to move a fluid from point A to point B, maybe under pressure, maybe not. Pipe threads are used in those applications to seal the thread joint around the threads so that the fluid moves and doesn't leak out the threads. These are called straight threads. They don't have a taper to them. Pipe threads have a taper. They're smaller at one end than they are at the other. They're still a 60-degree triangular profile, but they're smaller at one end than the other. And what that does is as you screw it in, it jams itself into the hole, the tapered hole, and the harder you twist, the more it jams itself. It actually bends and malforms the metal just slightly around these threads and jams it together, forming a seal. Okay? Now, a couple items of note. These are used for sealing applications, and they're used at extremely high pressures. You use pipe threads up to 10,000 psi or even more. Okay, so if you use the right material and the right thread, you can seal things at very high pressures. Now, commonly you'll see people put Teflon tape and wrap it around these threads. You've probably seen that before. That is not always necessary. Okay? It's not the Teflon that's doing the sealing. It's the thread profile that's doing the sealing. Most joints will seal without Teflon tape, no problem. Okay? Where you use the Teflon tape is where you have small molecule fluids. So if you're running water through there, water is a huge molecule. It's H2O. It's big. Okay? Air, huge molecules, mostly nitrogen and oxygen. Big molecule. Okay? But something like helium is a tiny molecule, or hydrogen. Okay? Very, very small. And those molecules can escape through these little crevices easier than other gases. In those cases, they put Teflon in there to kind of fill up any little tiny minuscule gaps. Another thing I want to say about tapered threads. With straight threads, you can screw in and screw out a lot of times. Okay? You can assemble and disassemble a lot of times. Here, because you're jamming this in to seal something, you are basically ruining the threads. You're bending the threads on a small level. So you cannot cycle this very much. 2-3 times, and that's it. Especially if one of the fittings is a harder material than the thing it's going into. Okay? You're going to ruin those threads and ruin that hole. Pipe threads are really mostly meant to be put in once and left. You're jamming it down, you're sealing your fluid, and you're leaving it alone, and you're operating. Okay? Another thing you might want to think of is coefficients of thermal expansion. Okay? If you're going to subject your fluid to temperature variations, either extreme hot or extreme cold, you want to make sure that your materials are the same, because if it's jammed together, but one material expands faster than the other under these temperature extremes, you may lose your seal in there. So as an engineer, you should always be thinking about coefficients of thermal expansion. Another thing about designations, okay? Pipe threads are designated just like regular threads. I think like a pipe thread is a 1/4 27. 1/4 inch, 27 threads per inch. Okay? That's going to be a 1/4 inch NPT. NPT, National Pipe Taper. Okay? The thing is, it's a very common mistake to make to think that that's a 1/4 inch in diameter. This metric or unified national, a 1/4 inch means about a 1/4 inch nominal. You throw calipers on it, it'll be about a 1/4 inch. With these threads, the 1/4 inch means this is the type of thread that will allow enough material under standard applications to screw into a material and seal it such that a nominal tube OD of a 1/4 inch can go through. Approximately a 1/4 inch. Okay? And that's so that you engineers can do fluid dynamics analysis on this. If this hole, the fluid going through here is about a 1/4 inch, that's what you care about with the fluid, is its cross-sectional area and its pressure to see how much fluid can jam through that pipe in a given time, right? So if this is a 1/4 and this is material to seal under potentially high pressures, what does that tell you about the diameter of these threads? A lot bigger than a 1/4. Okay? We could go measure one, but I think a 1/4 inch pipe fitting is well over 1/2 inch. I think it's close to 5/8 of an inch or something. Much bigger than a 1/4. Okay? So a common mistake for engineers is to say, well, I got a 1/4 inch NPT, so in my SolidWorks model, I make a hole a 1/4 inch. It's way bigger than that. All right, questions there? Those three, as engineers, you're going to use a lot. Unified National, metric, and NPT, or taper or pipe threads. Questions there? There's other thread forms. There's a whole bunch out there. You won't see them as much. Acme threads are for lead screws typically, and that's when you want to move something back and forth quite a bit. And they have this trapezoidal shape to them. Why do you think that is? Right. This tip right here, if I'm spinning at fast speeds and moving heavy loads back and forth using this screw, this drive screw, these little tips up here might bend over and get screwed up. In a trapezoid, they're not going to do that as much. So that's why they have that. They have threads called buttress threads, where instead of an isosceles triangle here, it's more of a right triangle. And that's for really high tensile loads in one direction, because you get a bigger length in this triangle here. So, different thread profiles. Bolts also come in different lengths, different diameters, and they come in right and left hand. So right hand threads is mostly what you guys are used to. So you've heard a right hand thread screws in if you screw counterclockwise or clockwise. So if you're looking at the head of the screw, you're turning kind of right. It's like your steering wheel in your car. If you want to turn the car right, you turn clockwise. So it's called righty-tighty, right? Lefty-loosey. Well, left-hand thread is the opposite. Okay? They use left-hand threads in quite a few applications. The first major application is on compressed gas regulators. Because it's dangerous to hook a flammable gas up to an oxidizer, they typically make flammable gas fittings like acetylene or methane or propane. They typically make those left-handed threads. Now they don't do it on propane tanks at your house because most people are morons and wouldn't understand what a left-hand thread is. So they'd all be coming back to the hardware store and saying, I can't hook my propane tank up. But you guys are engineers, so if you get into industrial stuff, they expect you to understand left-hand threads. So to prevent people from putting oxidizers with flammable gases, they use left-hand threads on regulators for flammable gases. You also use left-hand threads for applications where you might be spinning in one direction. and you want to, as this spins, you want to make sure that the bolt, if anything, would tighten, not loosen. So you might use a left-hand thread such that if it's spinning in that direction, it actually tightens that thread. And you can also use it in the case of turnbuckles. I'm going to show you a turnbuckle because most people don't know what it is. So for example, let's say a farmer or a rancher has a fence, and it's a wire fence with posts. And let's say he wants to tension the barbed wire, get it really tight. So they'll often use a turnbuckle. So they'll have, let's say, little loops here and a hook. And in the middle, they'll have what's called a turnbuckle, and it has right-hand threads on one side and left-hand threads on the other. And that way, if you turn this one direction, one of them will spin in and one of them will spin out. So what that does is it takes these two pieces and moves them out or moves them in opposing directions. If you had both right-hand or both left-hand threads, it would just move it one way or move it the other. But with a turnbuckle, backwards threads, when you turn it one direction, one will come in and one will go out. So they'll do this or they'll do that. Okay, so those are typical applications for left-handed threads. For a left-handed thread, you need a left-handed tack. For a right-handed thread, you need a right-handed tack. Okay? I'm going to make myself a note. Okay. I want to talk about something else, but I want the other group to see it too. Okay, they come in different finishes. We have black oxide. It's kind of a powder-coated finish. Zinc plated, that's an electroplating process where they ionize the metal, positively charge one, negatively charge some zinc powder. They attract to each other and they stick. Chrome plating, cadmium plating, Teflon coats, passivated coats. Most of those coatings are meant for resistance to corrosion or oxidization. Okay, so if you have a steel screw, you don't want it to rust. In a high humidity or a high, like a salt environment or something, but you need the strength of steel as opposed to a stainless steel or a brass. You might coat that with something to prevent corrosion. Screws and bolts come in different pitches. So in the unified world, pitches are threads per inch. In the metric world, pitches are millimeters per thread. So your metric pitches look like 1 millimeter per thread, or 0.5 millimeters per thread, or 0.25 millimeters per thread. In unified, you get things like 1/4 threads per inch, or 40 threads per inch, because an inch is a lot longer than a millimeter. Okay? You get tolerance classes. Okay? 1A, 2A, and 3A are the most common you'll see on drawings. And those are external threads like bolts and screws, male threads. 1B, 2B, 3B are the same classes but for female threads, internal threads. Okay? Class 1 threads are loose fitting, they're kind of sloppy, and they're meant to be that way so that it's easy to install them and take them apart. Okay? For people at home with their furniture or things like that, or even your cars. Okay? As you get to 2 and 3, what happens is, let's say this is the bolt. Okay, so a thread class 1 might look like this. A thread class 2 might look like this. And a thread class 3 might look like this. It's much closer. You have more engagement. It's a tighter tolerance needed to manufacture those pieces so that they'll fit. But if you're a closer fit and you have more surface area, you get more strength in that screw or bolt. So in some cases as an engineer, you may need to spec out a class 3 thread because you need that strength. Okay? We mostly deal with class 1s and 2s. When you see, in most cases, in order to make a certain thread class, you have to buy a certain tool. So you'll see on the tabs, you might see thread classes on the tabs, 1A, 1B, 2, or 1A, 2A, 3A. And on and on and on. Screws have all kinds of other parameters you can look at. One of the most common is material. So not all screws are made alike. Some screws are made for low load applications, and therefore their alloy of that steel is crappy. And if you put it into a high load application, it'll break. I don't know if you've ever heard of grade 8 bolts, but grade 8 bolts are a very strong bolt. It's a bolt that's the material, it's been heat treated, and it's meant for high load applications. Whereas you get kind of a zinc plated grade 3 bolt from Home Depot, it's only going to be so strong. So not all bolts are created equal. As an engineer, you have to know which one's which. Now, the most important, so there's a lot of parameters for screws and bolts. The most important things for you guys are so that you can dimension holes, pick the right size bolt for the application. And to do that, we use a couple of charts. First of all, we have the decimal equivalence chart, and you guys should either find yourself one that you really like or get yourself a reference like Machinist Handbook so you can have it in paper form, but you could bookmark it on a browser or something. This is an example of a decimal equivalence chart, and it's pretty good. The one in my shop is a little bit better because it has the screw sizes on there too, so that's pretty cool. But a good decimal equivalence chart will have a few things. First of all, it'll have the decimal equivalent. That's the definition of the chart. Whether you're in metric or you're in English units, they all have the decimal equivalent in common, and these are in inches. Okay. You will have fractional sizes. That's 1/8, 1/4, 3/16. Those go all the way through the chart. You will have wire gauge sizes, which are important because most of the holes that you're going to drill in order to run a tap to make threads through are going to be wire gauge sizes in aerospace because we use small screws for our small little satellites. Okay, so wire gauge sizes typically start at 80 and go all the way to 1. And here's your decimal equivalent. Then, in English units, we go to letter sizes after you go to numbers, and they go from A to Z. And then after that, we typically stay with fractional sizes. You see there won't be any letters or numbers, and we tend to stay with fractional sizes from there on out. A good decimal equivalence chart will also have metric units so that you can cross-reference. So if I have an M5 screw, there's a 5 millimeter, I can see what that approximately is in English units. So you probably might want to find yourself a good decimal equivalence chart. Like I said, in the shop, there's a little bit better one. A number 10 screw is right about in this range. So it'll put like a 1024 right there. Or it'll put on the tap drill for a number 7. A tap drill for a 1/4 thread is typically a number 7 in soft materials like aluminum and brass. They'll put a little 1/4 right there to tell you that that's the standard tap drill. So find yourself a decimal equivalence chart. As an engineer, that's an invaluable resource. The other thing that's useful is a tap drill chart, and this one happens to be in English units, and you can find them for metric units as well, and you can find them with both on them, so maybe you want both. But a tap drill chart will help you determine hole sizes, whether you're going to have a thread that screws in or a thread that just goes through. I'm going to make myself another. on a tap drill chart, for example, we have, oh, by the way, in America, we have all these screw sizes, but the standard ones tend to be evens. So we tend to have 2s, 4s, 6s, 8s, 10, 12s. You can find 3s and 5s, but they're hard to find. So try not to use odd wire gauge sizes. 2s, 4s, 6, 8, 10. In metrics, you don't have to worry about it. Although I found that metric screws tend to be also on the even size, at least on cars. They tend to use 10 millimeter, 6 millimeter, 8 millimeter, 12 millimeter. Not always, but they tend to use them. I don't know why that is. Okay, let's say I had a number 8 screw. On this tap drill chart, it gives me my approximate major diameter, and that means, here's my screw. That means from tip to tip on the threads. We call it the crest. So that nominal diameter should be about 1.164. And then I've got my coarse screw, which is 32 threads per inch, and my fine screw, which is 36 threads per inch. Okay, they give you the minor diameter, which is here. Sometimes that's useful. I'm sorry. It's here. Sorry about that. And then they give you the tap drill size for that thread, and they give it to you in soft materials and hard materials. And the reason for that is, if you're going to look at this triangle, on the soft materials they say go ahead and use a 75% thread. And what that means is that when you cut this thread, here's the bolt. When we cut this thread, the height is 75% of this overall height. And that allows you to be able to screw this thing in. Okay, for harder materials, they use less, it's 50% of that height, because the material is stronger, so it doesn't need as much material to give you the same amount of strength, and it's harder to tap a harder material like that. So they do a 50% thread, which gives you a smaller or a bigger drill size. You're going to drill a bigger hole, so you'll have a smaller engagement on your threads. They also have close fit and free fit. Those are for clearance holes, and we'll talk about that in a minute. But that's when you want to have a screw just drop through. You don't want it to thread in, you just want it to go in. You want it to go through the hole, and then you'll thread it into something else. All right, that's where we left off with the other group. Let's do another quick break, since it seems like you guys are done, right? Okay. Let's do, say, 10 or 12 minute break, so back at 11:35 here.